Hey guys, good morning. Hope you had a great weekend. We are going to go over chapter 3. Okay, so chapter 3 is on two variable stats, and basically it's going to review things that we did actually in grade 9. So in grade 9, we learned how to draw a scatter plot, so those are some things that we're going to talk about in this unit. It's a pretty short unit. There's only about, I would say, 9 sections, and within those 9 sections, I think it includes like 1 or 2 problem set days. So within that time, this is actually going to fly really quickly, and then we'll go into our chapter 4 and 5, which is on probability distribution. And again, I hope you're continuously working on that part of the culminating task that's due in May. So please continue to work on that. If you have any questions, we can always touch base as they come up. But keep in mind, I did upload a exemplar with a Microsoft Doc that you can actually edit once you download the document onto your own device. And you would type in your business proposal. And remember, be very fictional. Include lots of detail of who you are, what you represent, what you hope to find, and just take on that role and think about how would you go on with trying to figure out information for this case study that you have, and what kind of detailed information could you provide, with your company to help them solve through the issue that's at hand. Okay, so I'll go on with our lesson. So today we're going to talk about 3.1, which is on scatter plots and linear regression. I again apologize for any chicken scratch you might see. I know you guys know I write much nicer than what you see on the iPad. However, I'll do my best, and I can clarify anything as it comes. Okay, so I'll also post a blank copy. So in case you want to rewatch the video, complete the blank copy while replaying the video. That might be a good strategy for you as well. If you don't have a printer, you want to just write it out on your own side paper, you could do that. If you want to just view the good copy, that's okay too. Just giving you lots of options for your own learning styles. Okay, also I will be posting a Unit 3 booklet so you guys can look at your homework sets for today. So it would be under the scatterplot and linear regression portion. And you do need graph paper, okay? So if you have a printer, I have uploaded on Edsby different types of graph paper. So I have the 4 quadrants, I have just like the blank sheet of graph paper, and you can draw your own axes. If you don't have a printer, you might have your own graph paper, or you might just want to find some sort of online graphing system like Desmos where you can actually plot these coordinates. And you could also use Excel. Okay, Excel is actually a very, very good tool, and we'll go on to how to function through Excel in this chapter. You can use, I know there's so many different versions, and that's going to be a little bit trickier because I don't know what kind of computers you all have at home. So I know Microsoft Office does offer a version of Excel. Unfortunately, it does not have all the buttons and the necessary things that we may need for the entire course, but it might be good as a starting point. Okay? All right, so we'll get on to talking about 3.1. Okay, so in scatterplot and linear regressions, you might recall when you plot a scatterplot, it is always amongst a x and y axes. Okay, where your dependent variable and your independent variable are located on your x and y axes. So your independent variable is always going to be your x-axis. Okay, where your dependent variable is always going to be your y-axis. Now, statistics tries to discern whether one variable, the dependent or response variable, is affected by another variable, the independent or explanatory variable. So a really, small example of something that I generally teach my grade 9s when I talk about dependent versus independent variables is just this idea of, how are two things related in the real world. So you might think about a time when you have gone to the movies. Right? So if you go and you see a movie that, is debuting for the first time, the ticket sales would be, for instance, your independent variable. And your popcorn sales would be your dependent variable. So obviously, the more tickets that are sold, ideally the higher popcorn sales would also increase directly with that. Okay, so if you watch a new movie, it comes out, typically you might want something to snack on, so your popcorn sales would obviously go up. In most cases, people don't go to a movie theater to buy popcorn and not watch a movie. So we would say in that case, popcorn sales are dependent on the amount of tickets that are sold for this particular movie. Now, scatterplots show such relationships graphically. Now, sometimes they create different types of fit. So you might recall creating a line of best fit where the most amount of points lie on that linear line with an even amount above, below, and touching as many points as possible. So the line itself has to go through the data. Okay, so you might consider something that goes through the data. Sorry about the poor line there. And there might be different values that go around it. And of course outliers that are very far from the line itself. Okay, so we'll also talk about that in this unit. A line of best fit, so for your fourth bullet, is the straight line that passes as close as possible to all of the points on a scatter plot. So once again, it goes through the data. Regression is a process of fitting a line or curve to a set of data. So you might recall a line of best fit versus a curve of best fit is very different. It depends on how the data is represented. A line of best fit could be something that's represented here in my little diagram. A curve of best fit could be something that's parabolic or exponential. There's something called the correlation coefficient. Okay, and the correlation coefficient basically takes the scale from -1 to +1, and it measures what type of relationship is produced out of those two variables. Okay, so this is developed and known as the Pearson product moment coefficient of correlation, or Pearson's R, and it basically quantifies the linearity of a set. Okay, so for instance, measures that are exactly 1 would be something like this. This would have a correlation coefficient of 1. Okay, now the reason why it would be at 1 is because each point that I've drawn is touching that line. So this is a perfect positive correlation, or we would have called it back in the day, grade 9, a positive correlation, right? The strength would be very strong. There's also moderate, there's also weak, and that goes for the negative ones as well. Now, if I wanted to play around with those numbers, and I took a look at this graph, right, I would still say that that's a positive correlation. I wouldn't say it would be perfect, because as you can see, there are many data points that are close to the line, but not quite close. Okay, I would maybe say this would be a moderate, maybe even almost weak positive, because there are a couple points that are above and below. Okay, now when we make that, I guess, generalization, we're using numbers that apply to the scale. So you can see here it starts at -1 and goes all the way to +1. And a no correlation is smack in the middle. Okay, so no correlation would be something like this. Okay, so I just have a bunch of data that's scattered across my x and y axes. I don't know if it's increasing, nor do I know if it's decreasing, right? So that actually would have no correlation, because I can't tell if the relationship between the variables is one that's going up or if it's one that's going down. Okay. Now, perfect negative could be one that looks like this. Okay, sorry, that's so poor. Where every point is touching that line, however, you'll notice it's a negative slope or a negative line. So an example I like to use with that is if you go to a gas station, right, and you consider the distance traveled after you leave that gas station. Well, obviously when you go to the gas station, in most cases, you would fill up your car tank to, the amount that's needed for your car to be full. And then the more distance that you drive, the less gas is left in your car. So you'll notice that you have a negative relationship where your gas mileage is decreasing directly with the gas distance or distance that's taken as you proceed on your trip or wherever you're going, even if it's multiple trips. Okay, so what we're actually going to learn is how to calculate that R, that correlation coefficient. Okay, so to calculate R, you have this really long formula, but I'll go over what each of the variables mean. Okay, so for R is going to be equal to the number, so again, the data set, multiplied by the sum of x times y. Okay, so the sum of x times y subtracted by the sum of x multiplied by the sum of y, and that's all divided by the square root. And within that square root, there's two parts. There's the first part, which deals with your x data, and then the part that deals with your y data. Okay, so that's n times the sum of x squared, so squaring each point, taking that value, or that total, subtracting it by the sum of x, then squaring that value, and then multiplying it by the same thing, but now considering the y's, where you multiply the sum of values multiplied by the sum of y squared minus the sum of y, and then squaring that value afterwards. So we know how to do that because we did that in our standard deviation in Unit 2. Okay. So what we're going to do is we're going to determine the coefficient correlation for the following data sets. Okay, so we have temperature and we have crop yield. Okay, so as you can see, our temperature does represent your x values, and your crop yield does represent your y values. Okay, so this data is already organized for you, where all of your temperature values are already exported to your y column. Your crop yield is already exported to your y column. And what you're going to do is you're actually going to square all of your x's, square all of your y's, and then find the product of multiplying x times y. Okay, so I'll walk you through the first one. So we have x as 4, so obviously we would do 4 squared is equal to 16. Okay, because that would be the x squared value. We would do 1.6 squared, and that would be equal to 2.56. Check that one more time. Okay, and then you would find the product of multiplying 4 times 1. You're not agreeing with me today. Let's try that again. 4 times 1.56. Okay, and you would get 6.4. All right, so you can take a couple minutes to review and to actually work this out on your own. Okay, so again, you're squaring all of your x values, squaring all of your y values, and then multiplying the product of x times y as you go across horizontally on your row. Okay, and then what actually goes at the very bottom are our totals. Okay, so to find the sum of x, you would add up all of your x values. Okay, so in this case, we actually get 48. Okay, to find your sum of y, you would add up all of your y values. And in this case, we get 12.9. you would add all of the x squared values. So obviously you would have to had done this portion. Okay, so whatever you get for all of these values, I'll post the full solution so that you can compare yourself. But the sum of x squared in this case is equal to 418. The sum of y squared in this case is equal to 28.35. And then in your last column, the sum of xy is equal to 105.3. Okay, so now we're going to take all of those values and we're basically going to go back and think about how we determined earlier if it was a negative correlation, perfect negative, moderate negative, weak negative, if it had no correlation, and then up to the scale of perfect positive, weak, moderate, strong, or up to perfect, right? So we're going to input the formula here of r equals n sum of x times y minus sum of x times sum of y, all divided by the square root of n sum of x squared minus sum of x squared times n sum of y squared minus the sum of y, and then squaring that value all over the square root as I mentioned. Okay, so we're going to actually take that. I went ahead and just did that information ahead of time, so I'll just talk over it. So basically we took each of our values. Okay, so you'll notice here there are 6 data points, 1, 2, 3, 4, 5, 6. So that highlights why you have a 6 for n. Okay, for the sum of xy, right, that's at 105.3, our last column, so you see that in there as well. The sum of x is 48, the sum of y is 12.9. That takes care of your numerator. So I would always just write out your substituted values first, and then you can apply it to your calculator after. That's going to be divided by n, so again, n is equal to 6, multiplied by the sum of x squared, so 418, minus sum of x, which is 48, and then squaring that value. I put square brackets just to keep it all clean and nice. And then I'm going to do the same thing for your y portion, so 6 times 28.33 minus 12.9 squared. Okay. I just realized that should be 3. There we go. Sorry if that's not clear. Okay, so you work out your numerator, you work out your denominator. Don't forget to square root everything in your denominator only, and you should finish with a regression of 0.47. Okay, so that coefficient correlation means that if we're going to consider a line, get our color, right, of -1 to 0 to 1, and we get r is equal to 0.47, right? So that's in between of the range of basically weak to moderate. So even if we go back and look up at our scale, that's almost at about a moderate positive, okay? All right, so for example 2, I'll let you guys try out that portion on your own. It's pretty much the exact same steps, just with different data points. Again, it's already been imported into the appropriate columns for your x and y values. Okay, so once again, you will square your x's, you will square your y's, you will find the sum of x times y. You would find your totals. So again, sum of x, sum of y, sum of x squared, sum of y squared, sum of x times y. Okay, once you get those values, they should add up to the solution that I have posted here. Okay, where you get your correlation coefficient of 0.35. Okay, and just lastly, just a little information, just some things to go over with the correlation and linearity. So while Pearson's correlation indicates the strength of a linear relationship between the two variables, so once again determining how strong your x and y variables are, so how much does that dependent variable depend actually on your x variable? Does it have a close relationship? It's determined through how we calculated r. Its value alone may not be sufficient to evaluate the relationship. Consider the four relations below known as Anson's quartet. Each relationship has the same mean, standard deviation, correlation, and regression line. We will talk about how to create that y equals mx plus b look of a regression line. Okay, and you might notice that, again, basically what this is trying to indicate is that although we find r, our correlation coefficient, it doesn't mean that that solely represents how close a relationship is, right? As we know in data management, when we use these calculations, they're basically indicators to help demonstrate what type of relationship is at hand when we're looking at something. Right? It doesn't particularly mean that if we use this one method, that's the be and all of all of the, I guess, the way we wrap up that idea, and that that's the only way it can be interpreted, right? So similar when we were doing mean, median, mode, right? Depending on how the data was represented, it doesn't mean that we just find the mean and that's the only thing that we look at. We looked at how to calculate the range, the median, the mode, and so forth. Okay, so we'll talk about this more within this unit. Okay, correlation and causality. So establishing a correlation between two variables is not a sufficient condition to establish a causal relationship. So for example, hot weather may cause both crime and ice cream purchases to increase, but it does not mean that crime is correlated with ice cream purchases. But crime does not cause ice cream purchases, and ice cream purchases do not cause crime. So again, in this unit, we will be looking at cause and effects of different relationships and really digging deep and trying to determine what type of relationship that they have. But again, this last page just tells us to keep an open mind as we calculate different things in our Unit 3, two variable stats unit. Okay, so hopefully everything in here was clear. Okay, once again, you will be completing your own homework set solutions. You will need graph paper for this unit. As you can see, we are looking at two variable stats and looking at scatter plot, so it would be helpful for you guys to have graph paper. If not, again, you can just spend some time with a ruler, creating your own grid, doing that stuff. Yeah. Okay, so hopefully this was helpful. Let me know if you have any questions, and honestly, I miss you guys so much. I hope you guys are staying well. Okay, take care.